So next talk is entitled Full Threshold Actively Secure Multiparty Arithmetic Circuit Garbling by Eleftheria Magri and Tim Wood. And Eleftheria will give the talk.
Thank you. We heard from the very beginning today of the workshop about active security and the importance thereof. So I don't need to argue about this part. So Karmit has covered that. So I'm going to talk to you about how we can garble arithmetic circuits with active security, and I will focus on one specific gadget, one specific gate that we improved. But what about garbling? We didn't hear the general story today of the garbler and evaluator yet. So traditionally, we are talking about a two-party protocol where we have the garbler and then the evaluator. And we wish to construct a protocol so that they can evaluate a function together without anything being revealed about the inputs of the one party to the other than what can be inferred from the output. As David pointed out, the challenge here is the communication complexity. So we like garbled circuits because we can construct constant round protocols with them. And from a computation perspective, they have nice features because they use only symmetric primitives, essentially PRF evaluations, which are cheap. So what we are trying to improve is indeed the communication complexity. Now, let me first guide you through the history of garbling. So garbling was invented by Yao in 1986. And then we had already the first optimization by Beaver et al. In 1990, the point and permute, and they also showed how we can do multi-party garbling for the first time. Then we have the next optimization in 1999 from Naor et al. Showing how we can reduce from 4 to 3 garbled rows for the gates. Then in 2008, free XOR appeared, and in 2009 we have another optimization of row reductions, which goes from 3 to 2 rows. In 2014 we had the FlexOR, trying to combine the best of both worlds, so trying to have 2 rows for AND gates and still get the efficiency that we have from free XOR, but we are not quite there. So it depends on the circuit structure, how many ciphertexts we actually need for the XOR gates. And then eventually we do get the best of both worlds by Zahur et al. In 2015 with the half gates. In 2016, we have another set of BMR authors, Bol et al., officially showing for the first time how to do arithmetic garbling. So all the work until 2015 was on Boolean garbling. And they also showed how we can do high fun in Boolean garbling. Up to this point, we mostly talk about two-party garbling. So the paradigm I showed at the very beginning, garbler and evaluator. And in 2018, Ben Ephraim started showing also how we can do multi-party garbling, and especially focusing on using the arithmetic gadgets that we got from BMR 16. And he also showed how we can optimize a selector gate, what he calls a selector gate, from the standard construction to a better version, so to say. In 2019, we had again from Bol et al. Another garbling paper where the focus was on constructing garbling circuits for neural networks, but the main gadgets in this work were mixed modulus half gates. So how can we do half gates where the wires come from different fields, live in different fields, and how can we do mixed radix addition? And then comes our work. It's a joint work with Tim Wood, where we show how we can do multi-party arithmetic garbling with active security with n-1 dishonest parties. And we also show an alternative construction for the selector gate that Ben Ephraim proposed. So just for comparison reasons, yeah, what we add to the table is the full threshold active security compared to the previous work, and a different construction for the selector gate. Now, in the meantime, other important things happened unrelated to Garbling, and that's why we are now sitting behind a screen for TP-MPC this year. And let me summarize now from a cost perspective the optimization I mentioned before. So I stay up to 2015 because these are the works that talk about Boolean garbling, and I will present the optimizations in the arithmetic garbling later on. So for every gate from classical garbling, we had to send 4 ciphertexts per XOR gate, as well as 4 ciphertexts per AND gate. Then the garbler has to garble all 4, and the evaluator has to decrypt all 4. Then we have the point and permute optimization, which allows the evaluator to decrypt only 1 of the 4 rows. And then we have the garbled row reduction later on, which allows us to send 3 ciphertexts instead of 4 per gate. So from that moment on, everything is compatible with the point and permute. So I'm not repeating this. We have the same optimization. Then from Kolesnikov and Snyder, we got the free XOR, which is actually compatible with the garbled row reduction 3. So we need 0 ciphertext for the XOR gate and 3 ciphertexts for the AND gate. And then we have the garbled row reduction to 2, but unfortunately it is not compatible with the free XOR technique. Trying, as I said, to bridge both the best of both worlds, we have the flex OR, where the number of ciphertext per XOR gate depends on the circuit structure. And finally, we achieve what we wanted in the first place with the garbled row reduction 2, to have both free XOR and only 2 ciphertexts per AND gate. So what's next on my agenda for today? I would like to present to you the selector gate. First, I will explain what that is and what Ben Ephraim did, and then I will explain our optimizations on that. Then I want to tell you how we achieved full active security in that setting for n-1 dishonest parties. But before all that, I would like to start with explaining what is this half-gate multiplication, because it's a very important component for the explanation of the selector gates. So I'm removing a lot of details from the formulas from that moment on, so I'll try to do it at as abstract level as possible. So I will try to explain what is half gates, both in the Boolean case where we talk about AND gates, and in the arithmetic case where we are talking about multiplication. So what we want to compute at, with a half gate is the same result as a multiplication. We want to know the external value EZ at the output wire of the gates. The external value has to be the sum of the real value on this wire and a permutation element that we denote as lambda z. So that would be a bit in the AND case. It would be a FP element in the arithmetic case. And we want this real value to be the product of the real values on the input wires X and Y. Okay, so that's what we need to compute. How do we do that? We do it by splitting the problem into 2 half gates, because we are trying here to exploit the asymmetry between the garbler and the evaluator. We're trying to take advantage of the fact that the evaluator knows different things than the garbler. So we have 2 gates, the first and the second half gate, and as you can clearly see from the equation, this adds up to what we want to compute, Vx times Vy. Now, the paradigm with the 2 parties is nice, but not everything works in the multi-party setting. In the multi-party setting, the the Garbler cannot know the permutation elements lambda z because all parties play the role of the Garbler here. So what we do to achieve privacy is to split the permutation elements into two parts. We call them lambda z tilde for the Garbler and lambda z hat for the evaluator. We actually do the same things for the 0 keys on the output wire, but since I'm omitting a lot of details, you don't need to remember this for the rest of this talk. Okay, and how are we gonna then garble and compute this external value? We are going to take these half gates we split before and add the corresponding permutation elements. By the way, I didn't mention these permutation elements have to be random, but they have to add up to the lambda z, of course. The permutation element at the output wire. So we have the Garbler half gate and the evaluation half gate, and we exploit the fact that here we have the external value on wire y that is known at evaluation time at the evaluator, and here we have the permutation element on the y wire, which is known at the Garbler at garbling time. So with this trick, and given that the free XOR extends to the arithmetic case, we can compute the multiplication gate based on these two half gates. Now, now we have the basis. Let's go to selector gates. First of all, what is a selector gate? A selector gate takes two inputs in FP, x0 and x1, and one input and one Boolean input. I denoted B here, and it outputs one of the two values in FP based on the bit input. So following the same paradigm with green and red that we saw from David before, when our bit is 0, we output x0, and when our bit is 1, we output x1. All right, so how would we garble a selector gate? I'll start with a straightforward construction. First of all, we need to be able to project this bit to FP so that we can work with the other two inputs. That's what I denote here by phi, this projection, and I follow Ben-Ephraim's notation. So VW0 is the real value on the Boolean wire. So you can see that if I follow the first equation, I get the required result. So I get the selector utility. But I, first of all, would like to have as few projections as possible. So that's the first transformation, to only have to do one projection of the bit and not also the projection of the inverse. And then I would like to have as few multiplications as possible. So if I rewrite this equation, the problem boils down to computing one projection and one multiplication, given that I can compute the difference between x and y and freely add the real value on the y wire. So these, I remind you, are an extension of free XOR, so we can do them locally for free. So essentially what I want to be able to do is to do a projection from F2 to FP. So compute again the external value on the output wire, which is the real value plus the permutation element. So how are we going to do this? So if the external value on the Boolean wire is 0, this means that the real value is equal to the permutation value, to the permutation element. So this means that since this is 0, if I just simply add the value of the permutation element, what I get as a result is the real value on the wire. So I can simply add the new permutation element in FP. Now, if the external value on the Boolean wire is 1, then I know that these two values are different from each other. So if I simply subtract given that the external value is 1, if I simply subtract the permutation element, what I get is the real value on the wire. So again, I simply add the lambda z and we get the desired result. So after this point, so since we know now how to do this projection, we simply need to do this multiplication based on half gates. Now, what's the cost of this? In terms of numbers of ciphertexts, we need 2 ciphertexts for the projection gate and 2 times p ciphertexts for the multiplication. That is based on half gates, so p plus p ciphertexts. Now, at the evaluation time, we need to do 3 decryptions in total. So this is what Ben Ephraim tried to improve in his work. So let's see how he did that. I'm just showing you the same equation here as before for the selector gate, with just removing the phi's for the projection. So it's exactly the same thing simplified. And what I want to point out here is that we can actually do a half selector gate. So a half selector gate is a selector gate that gets 1 FP input and 1 Boolean input, and it outputs either the FP input or 0 based on this Boolean bit. So if I consider this difference as my input, I can simply garble a half selector gate and I will get the same result because subtraction and addition are essentially for free. Okay, so again, it's the same idea as before. Based on the external value on the Boolean wire, we can decide in which of the 2 cases we are, whether we need to garble the plus the permutation element or the minus the permutation element. So you see some extra here, lambda z hat and double hats. I'm not going into the details about that. They have to be there for privacy reasons. And inspired by the half gate construction, Ben Ephraim said, now we can split the problem in 2 and have chooser half gates and corrector half gates. And this would mean that we can actually, at evaluation time, have fewer decryptions to do. So the communication cost here is the same, but based on the chooser gate, we can decide in which of the 2 cases we are. So at evaluation time, the evaluator doesn't need to decrypt both of the corrector gates, but only one suffices. And that is the optimization here. Now, what about our selector gate? So the intuition behind our selector gate is, again, inspired by the half gates. So for standard multiplication, we need to do p times p. We need to send p times p ciphertexts. For a half gate multiplication, we need to send p plus p ciphertext. So our intuition says that if we have to multiply a bit by an FP value, we should be able to do it with roughly p plus 2 ciphertext. So how can we construct this? We are based on the simple observation that you can denote XOR essentially in any field by this equation, x plus y minus 2 times x times y. And by exploiting this property, we can do the projection directly. So first of all, we need what we call what Ben Ephraim calls multi-field shared bits for the permutation elements. That's actually implicitly used also in Ben Ephraim's construction. So we need to have given a bit in F2 to be able to project this to FP. We need to have a double wire mask for this bit. So lambda b prime and the lambda b that are equal, but the one lives in F2 and the other in FP. Then how do we do this direct projection gate? So we exploit the property of the XOR that I showed before, and we simply add the permutation element in FP. And that would be the external value on the new projected external value. Why is this useful? Because now we don't need to have p values for the external, p possible values for the external value, but only one. So the evaluator gets either lambda b or lambda b plus 1, but he doesn't know which one he got. And essentially afterwards, we simply do multiplication based on half gates. So again, I show you the same Garbler half gate and the same evaluator half gate. And here the evaluator knows the external value on the Boolean wire, and the Garble here can reconstruct from the shares the permutation element on the Garbler half gate, and therefore they can compute the selector gate result. Now, what's the gain here? Instead of having to send 2p plus 2 ciphertext, we actually need only p plus 4, 2 for the projection gate, 2 for the Garbler gate, and p for the evaluator gate. All right, so how do we achieve full threshold active security? We followed the blueprint of previous work by Hazai et al. On the Boolean setting. So the blueprint is first find a way to do authenticated sharings of the permutation elements on the wire and their product, then do a correlated oblivious transfer using correlated oblivious transfer protocol, do the products between the global differences on the wires and the permutation elements, and then only local computations and openings of sharings follow. And we had to translate this to the arithmetic setting. So we came up with a functionality FMPC instead of BitMPC to do the same thing for arithmetic. And then we replaced the correlated oblivious transfer protocol with a correlated oblivious product evaluation protocol. But as you can see, notational, they are the same. And we proved security thereof. So let me show you what we improved. What are the comparisons now for the arithmetic Garbling case? So we so far have two protocols for the two-party case and two protocols for the n-party case. All previous works are passively secure, while ours is actively secure. And what we managed essentially to achieve is almost half the communication cost of the previous work in the multi-party setting. So we go from 2p plus 2 ciphertexts per party to p plus 4 ciphertexts per party. But at the same time, we are losing the advantage that we got from Ben Ephraim's construction, where instead of the straightforward 3 decryptions, he managed to reduce to 2. This doesn't straightforwardly generalize to the 2-hour setting. So you can either split the problem vertically or horizontally, it seems, with a chooser and corrector gates. So let me close with some open problems. It seems very interesting. We heard already today the world neural networks. So it seems for many different problems interesting to have a conversion between Boolean and arithmetic circuits in the multi-party setting. I talked about projection gates also in the multi-party setting, but they have to be tailored, unlike the two-party setting where the constructions are more straightforward. So that would be nice to see what other functionalities we need to do with projection gates in the multi-party setting. And then it would be nice to integrate these optimizations together so that we can have circuits that can combine both Boolean and arithmetic parts. And of course, I didn't mention it, but there is some CRT-based optimizations in BMR16, and that would be nice to see how we can prove them secure in the active security model and in the multi-party setting. Thank you very much for your attention.